Hello, and welcome to a calculus lesson on continuity. It's the third topic of 4 in the Limits and Continuity unit. In Lesson 3a, we'll learn about continuity at a point, the formal definition of continuity, and discuss the 4 ways that functions fail to be continuous. The next lesson will focus on the intermediate value theorem. Let's get started. Here's a question for you. What does the word continuous mean in normal English contexts? In a moment, pause the video, think about the question, and write down your response. You can think about how the dictionary might define it, but it might be easier to think about its meaning in a normal conversation. Here goes. Pause, think, then write. Take about a minute. I invite you to write the meaning in the comments. Here are a few responses from students in the past. Continuous means goes on forever. Continuous means without breaks. Continuous means ongoing. Maybe you are thinking something similar. Now let's get more specific with the meaning of the word continuous in the context of calculus. Let's check out this rational function that has a few discontinuities. I hope you can agree with me that this function is mostly continuous. It goes on forever to the right, it goes on forever to the left, but at x equals -4, there's a hole, and at x equals +4, there's this big break, there's this vertical asymptote that's messing things up. Based on an informal definition of continuous, this function can't be continuous. But there are windows or intervals in which this function is continuous, and I could pick a bunch of specific points in which there is continuity, like x equals 0. And that, my dear mathletes, is the most important use of the word continuous in calculus. Continuous, or continuity at a point. Let's prove that this function is discontinuous at x equals -4. First, let's take the limit as x approaches -4 from the left side. I'll put my pencil on the curve to the left of -4, and let's approach -4 from the left side. And it looks like the y value is approaching some real number that's negative, but very close to 0. Then we'll take the limit as x approaches -4 from the right side. I'll put my pencil to the right of -4 on the curve and approach -4 from the right side. It looks like the y value is arbitrarily approaching a negative number, but a number that's very close to 0. Using a table with delta x set to 0.001, we can see that the y value approaches -0.125. That means the two-sided limit exists and it's -1/8. But that doesn't mean the function is continuous at x equals -4. It just means that the two-sided limit exists. The last thing we need to do is plug in -4 into the function to see what it gives us. When we do that, we get 0 divided by 0. When the two-sided limit exists and the function is undefined at that point, then there's a hole. Let's formalize that definition of continuity. Then we'll look at a few other ways that functions fail to be continuous at a point. The formal definition of continuity has 3 parts. These are based on a closed interval such that the left endpoint is called A, the right endpoint is called B, and there's some point in between A and B that we'll call C. If we're working with an interior point, we'll do exactly what we just did. We'll find the two-sided limit as x approaches C and verify that it's equal to the function's value at C. Notice that finding the two-sided limit as x approaches C requires that you find the left-hand limit as x approaches C and the right-hand limit as x approaches C. If you're working with a left endpoint, you're verifying that the limit as x approaches A from the right side of the function is equal to the function's value at A. Since it's a left endpoint, there's either nothing to the left of that point, x equals a, or we don't care about it. Similarly, if you're working with the right endpoint, you're verifying that the limit as x approaches b from the negative side, from the left side of the function, is equal to the function's value at b. This table is designed to help you visualize the interval with a on the left, b on the right, and c somewhere in between. We've arrived at the last part of this lesson, classifying discontinuities. Before I classify the discontinuities that these functions have, I invite you to use the comments to ask a question or share some feedback. Something you like or something that can be improved. If you like the video in general, click that like button. Okay, back to the graph and the 4 ways that functions fail to be continuous. The first one is a removable discontinuity, a hole. We saw this in the function that we looked at earlier. There was a hole at x equals -4, but why? Well, it's because the factor x plus 4 shows up in the numerator and in the denominator. And when that factor is 0 at x equals -4, then the function is undefined. Notice that there's another discontinuity with this function, but we'll talk about that in just a moment. The next type of discontinuity is a jump. It is just as it sounds, and we can see that in this function, the absolute value of x divided by x. If I put my pencil at a point on the left side of the function and move to the right, the only way to get to that upper right part of the function is to actually jump up. It's not considered a hole because the only way that you could patch that area in between the 2 parts of the functions is to plot an infinite number of points there. And if we do that, it won't be a function anymore. The third type of discontinuity is an infinite discontinuity. Here we have the secant function, which is 1 over cosine x. I use zoom trig for this window, so each tick mark represents a shift of pi over 2. So at every odd pi over 2, we have a vertical asymptote. Since secant x is the reciprocal of cosine x, I can actually sketch the cosine curve in between the secant curves. Secant x has an infinite discontinuity when cosine x is 0 at pi over 2, 3 pi over 2, and negative pi over 2, and negative 3 pi over 2. Infinite discontinuities also show up in the function 1 over x and tangent x. Finally, we have oscillating discontinuities. These are kind of weird, and they usually show up with trig functions like this one, sine of 1 over x. To get this graph, I did a zoom trig and then I zoomed in once. I can see that this function is oscillating a lot near x equals 0, but I'm not really sure what's happening at the origin, so I'll take a look at the table. First, I set up the table with delta x being 0.01 and the table start at x equals 0, and then I just arrowed down a bit. For x values less than 0, you can see that the y values go from 0.13, then they decrease to -0.9, and then they go up to 0.5. They do a similar thing for values that are greater than 0, but this is more than just a jump from 0.5 to -0.5. It's almost like a combination of a jump and an asymptote. So that's why I think it's kind of weird. The main 2 things to notice are the function is oscillating, going up and down a lot, and the function is undefined at x equals 0. That's it for discontinuities. In the derivatives unit, you'll learn 4 ways that a function fails to be differentiable. One of those ways is having one of these 4 discontinuities.